Good day, everyone. We are Team Europium and we will discuss the sample preparation for analysis. For the outline of this presentation, Nicole Vidal will cover the basics of sampling, including designing an effective sampling plan. Gerard Banaag will explain the different types of analyte separation techniques and the fundamental principles behind each of them. Desiraya Quizana will explain the fundamentals of the theory of separation efficiency. And lastly, Ron Fabian will explain and compare separation versus pre-concentration. But before that, I will provide a brief introduction of what is sample preparation in analysis and its importance. So what is sample preparation for analysis? Sample preparation involves extracting a representative material from a larger amount and preparing it for analysis. It improves the matrix by releasing analytes, removing interfering elements, concentrating or diluting the matrix if analyte levels are too low or too high, and chemically altering analytes for improved sensitivity. This improves accuracy, reduces the risk of distortion, and minimizes contamination during analysis.
Let us discuss the basics of sampling and designing a sampling plan. In a chemical analysis, results obtained are meant to be indicative of a concentration in a large system. For example, to determine the concentration of mercury in a lake, water samples are obtained and is taken to the laboratory for analysis. If the concentration is determined to be 6 ppm, then considering that the sample is representative of the entire body of water, then the lake is assumed to be 6 ppm in mercury. The process of obtaining a representative sample for analysis involves selecting representative sampling units or increments, collecting them to form the gross sample, then reducing the size and homogenizing the gross sample to create the laboratory sample, and ensuring that both the gross and the laboratory samples closely resemble the average composition of the total material. These steps are essential for obtaining reliable and meaningful analytical results. In order to minimize sampling errors, samples must be of an appropriate size. For instance, let's assume that our target population is a homogeneous mixture of two types of particles. Particles of A has a fixed concentration of analyte, while let's assume that particles of B are free of analytes. Samples from this target population follow a binomial distribution. Upon collecting a sample of n particles, the expected number of particles that contain the analyte Na is given as this equation, where P is the probability of selecting a particle of type A. The standard deviation for sampling is given as this, and to determine the relative standard deviation for sampling, we divide this by the number of particles containing the analyte, obtaining this equation. Solving for n, we can calculate the number of particles we need to provide a desired relative sampling variance, given as this equation. Apply this to a given situation. An analysis of soil where the particles containing the analyte represent only 1 times 10 raised to negative 6% of the population, a very small number, and we must compute how many particles must we collect if the desired relative standard deviation is 1%. Since the particles of interest account for only 1 times 10 raised to negative 6% of all particles, P will be equal to 1 times 10 raised to negative 8. Solving for n, we obtain this, which gives us 1 times 10 raised to 12. Therefore, to obtain a relative standard deviation for sampling of 1%, we need to collect 1 times 10 raised to 12 particles. Realistically, though, we can assume that both of the components in the mixture have the analyte, but in varying levels of concentration. The particles categorized as type A possess a greater proportion of the analyte, and particles of type B contain a lower amount of the analyte. The average density of these particles varies from the densities of the components. With this, we can decide that what number of particles and ultimately what mass we should take to ensure that we obtain a sample with the overall average percent of active ingredient P with the sampling relative standard deviation of S sub r, extending the equation to this. We can further rearrange this equation to calculate the relative standard deviation of sampling. Assuming that the sample mass is proportional to the number of particles and the other quantities are constant, the product of m and the sampling relative standard deviation should be a constant. This constant is called the Ingelmill's sampling constant. When the relative standard deviation is 0.01, SR times 100% is equal to 1%, and the sampling constant will be equal to m. Hence, we can interpret that the sampling constant is the minimum sample mass required to reduce the sampling uncertainty to 1%. This time, we should consider the number of samples to be collected in developing a sampling plan. If the results from an analysis of samples are normally distributed, then the confidence interval for the sampling error is given as this. Dividing the last term by the mean value, we can calculate the relative uncertainty that is tolerable at a given confidence level. And solving for n sub samp, we obtain the number of samples as this. Let us apply this to an analysis of copper in wastewater, wherein it gave a mean value of 81.72 micrograms per liter and a standard deviation of 1.74 micrograms per liter. How many samples must be analyzed to obtain a relative standard deviation of 1.7% in the results at the 95% confidence level? We begin by assuming that we have an infinite number of samples, which corresponds to a t-value of 1.96 at the 95% confidence level. Plugging in the values, we can obtain the number of samples as 7.66. Rounding the result to 8, we find that the value of t for 7 degrees of freedom as 2.365. Using this t value, we then find a second value for n, which is 11.2. Again, using 10 degrees of freedom, and at t at 2.228, the next n value would be 9.9. The iterations converge with an n value of approximately 10. When devising a sampling plan, it is also crucial to consider minimizing the overall variance in the analysis. The overall variance depends on both the method's variance and the sampling variance. Enhancing the sampling variance is achievable by gathering more samples of appropriate size, while analyzing each sample more frequently improves the method's variance. If the sampling variance is significantly greater than the method variance, we can ignore the method's contribution to the overall variance. However, if the method's variance is significantly larger than the sampling variance, then only one sample needs to be collected and analyzed. The formula for determining the number of replicate analysis required to minimize the error due to the method is given as this. Unfortunately, for the situations I previously mentioned, they are often not the norm. In numerous analyses, both the sampling variance and the method variance are substantial, necessitating both the collection of multiple samples and conducting replicate analysis for each sample. The overall error in such cases is given as this equation. Let's try to use this equation given a chemical analysis. An analytical method has a relative sampling variance of 0.50% and a relative method variance of 0.080%. Evaluate the percent relative error if you collect 5 samples and analyze each twice, and if you collect 2 samples and analyze each 5 times. Both sampling strategies require a total of 10 analyses, and from the critical values for t-test, we find that the value of t is 2.262. The relative error for the first sampling strategy would be 0.74%, while the second sampling strategy would yield an error of 1.14%. So based on our calculations, which sampling strategy should we consider and why? Well, as we discussed earlier, since the method variance is smaller than the sampling variance, we obtain a smaller relative error if we collect more samples and analyze each sample fewer times. Therefore, we should consider the first sampling strategy during this analysis.
Knowing the basics of sampling, let's now move on to analyze separation techniques and their classification. Separation is vital for synthesis, chemical analysis, and other fields of chemistry. It is utilized to isolate the analyte from interference that can affect the signals. Separation can either be complete or partial. In the diagram below, the components in complete separation is completely separated and they occupy various spatial regions. In the partial separation, only certain component is separated from the mixture. In this table, we can see different separation techniques and their bases. Let's discuss them one by one. Discuss separations based on size, since it is the simplest physical property that we can utilize in separation. One example of separation based on size is filtration. Using the separation technique, a filter is used to separate a particulate interferent from the soluble analyte. Some examples of filtration are gravity filtration, suction filtration, and membrane filtration. The next one is dialysis. In this separation technique, a dialysis membrane is made from cellulose, and separation happens because of the difference in concentration of species, causing diffusion across the membrane. In the dialysis membrane, small pieces can pass through, while large pieces cannot. One notable use of this is kidney dialysis, where blood is separated from metabolic waste. Lastly, the size exclusion chromatography. This separation technique utilizes a column that is made from 10 micrometer polymer bits of cross-linked dextrin or polyacrylamide, and more cross-linking means more small pore size. In this separations, the sample is passed through the column and the smaller molecule is trapped in the pores of the column where larger molecules can pass through the same rate as the solvent. This technique is commonly used in analysis of polymers or separation of proteins. The next one is separation based on mass or densities, and centrifugation is possible in this scenario. In this technique, the sample is placed in a centrifuge tube and it's spun at high speed. The species that experiences greatest centrifugal force will be the one to settle at the bottom first, since they have greater sedimentation rate. If the species have the same densities, the ones with greater mass have the higher sedimentation rate, while if the species have the same masses, the ones with greater densities have the higher sedimentation rate. One example of this is separating cellular components. Let's discuss separation based on complexion reaction, or also known as masking. Technically, it's just a pseudo-separation technique since we are just chemically isolating the interferent from the analyte in a solution using masking agents, and we do not physically separate the analyte from the interferent. In the table, we can see various masking agents and the elements they are masking. Part of the video, we'll discuss separations of analyte and interferent based on the physical changes of the sample. The first one is distillation that is applicable when the analyte and interferent are two miscible liquids with significantly different boiling points using repeated vaporization and condensation. Simple distillation apparatus is only for separating volatile species with non-volatile species, while fractional distillation provides more opportunity for complete separation. The next one is sublimation, and it is used when the sample is solid. In this technique, the sample is heated and pressurized just below the analyte's triple point for it to sublime and the paper is condensed to collect the purified analyte. One example of this separation of amino acid from fossil mollusks and deep sea sediments. The last one is recrystallization that is only utilized for purification of solids. In this technique, the solvent used is based on the significant solubility of the analyte when the solvent is heated and interference must be insoluble to it. This is done by repetitive addition of the solvent and sample in an Erlenmeyer class, and the insoluble impurities are removed via filtration and is repeated until all the sample is dissolved. The solution will be cooled down for crystal growth and the sample is purified by filtration, rinsing, drying, or further recrystallization. One separation based on changes in chemical state that relies on separation of analyte and interferent on chemical reactivity. The first one is precipitation and requires significantly different solubility of the analyte and interference. The feasibility of separation is based on solubility calculations. Various precipitating agents are used for quantitative and organic separation. Now, electrodeposition strength versus selectivity. In the separation technique, the quantitative result depends on various factors like electrode potential, electrode size, deposition time, and the stirring rates of the sample and calibration solution. The last part is volatilization, using heating or chemical disposition in order to separate volatile compounds that result in mass change, which can be used for analysis. One example for this is determination of hydrogen carbonate content of antacid tablets. The last part of this video, let's talk about separation based on selective partition of the analyte and interferent between two immiscible phases. Let's start with extraction, and it's a process of moving one species from certain phase to another, and it's helpful when one component has favorable partition coefficient. Some examples of this technique are liquid extraction that commonly uses a separatory panel, solid phase extraction that utilizes adsorbent materials, and continuous extraction for analyte with unfavorable partition coefficient using succulent extractor. The last separation technique that we'll discuss is chromatography. It's a well-known separation technique utilizing stationary phase and mobile phases. It relies on the difference between the migration rate of mobile phase components. There are two types of chromatographic methods, column and planar chromatography. One difference of the two is the mobile phase in column chromatography is influenced by pressure or gravity, while the mobile phase in planar chromatography is influenced by capillary action or gravity. Answer this question. Upon learning the separation technique, which the following occurrences does not complement the process of separation? A. Spatial distribution. B. Chemical reaction. C. Transport of materials. D. None of the above. Feel free to pause the video as you think of your answer. The correct answer is B. Chemical reaction.
The following topic will be about fundamentals on the theory of separation efficiency. The aim of an analytical separation is to remove the interferent or the analyte from the sample matrix. The analyte and the interferent must have at least one significant difference in their chemical or physical characteristics in order to successfully complete the separation. However, even possessing a significant difference in characteristics is insufficient for achieving separation if the circumstances that aid in the extraction of interferent from the sample also lead to the removal of a small amount of analyte. There are two factors that limit a separation's efficiency, which are failing to recover all the analyte and failing to remove all the interferent. We define the analyte's recovery Ra as Ra equals Ca over CaO. Ca is the concentration of the analyte that remains after the separation, and CaO is the analyte's initial concentration. The interference recovery Ri is defined in the same manner. Ri equals Ci over CiO, which is Ci is the concentration of interference that remains after the separation, and CiO is the interference initial concentration. The extent of the separation using a separation factor is defined as Si equals Ri over Ra, wherein Si is the separation factor. In general, a separation factor of approximately 10 raised to negative 7 is needed for the quantitative analysis of a trace analyte in the presence of a macro interferent, and a 10 raised to negative 3 when the analyte is and interferent are present in approximately equal amounts. Lastly, the potential effectiveness of a separation can be assessed with the use of recoveries and separation factors. However, these methods cannot directly determine the error that arises from incomplete analyte recovery or from failure to remove all interferent. The relative error due to the separation, E, is as follows. E is equal to S samp minus S star samp over S samp, where S star samp is the sample signal for an ideal separation in which we completely recover the analyte. It is defined in the equation below, where it is equal to Ka multiplied by CaO. Substituting this equation into the relative error due to separation E equation will be seen here on the right side. And a more useful equation is obtained by solving interference recovery, Ri equals to Ci over CiO for Ci, and substituting into the equation above it. The first term of the final equation would account for the analyte's incomplete recovery, and the second term accounts for a failure to remove all the interferent. For the practice problem, you may pause the video before we reveal the final answer. It is stated here that an analytical method for determining copper in an industrial plating bath gives poor results in the presence of zinc. To evaluate a method for separating the analyte from the interferent, samples with known concentrations of copper or zinc were prepared and analyzed. When a sample of 128.6 ppm copper was taken through the separation, the concentration of copper that remained was 127.2 ppm. Taking a 134.9 ppm solution of zinc through the separation left behind a concentration of 4.3 ppm zinc. Calculate the recoveries for copper and zinc and the separation factor. For the solution, using the analyzed recovery RA and interference recovery II equation, will give for copper is 1.9891 or 98.91% recovery. And for zinc, it is 0.032 or 3.2% recovery. The separation factor is calculated as given, and it gives a separation factor of 0.032.
Now let us discuss what is preconcentration and separation. What is preconcentration? Preconcentration is a technique that increases the concentration of a specific analyte in a sample before analysis, enhancing sensitivity. Common methods include solid phase extraction, liquid-liquid extraction, and cloud point extraction. After preconcentration, the concentrated analyte is eluted, desorbed, or released for analysis. And what is analytical separation? Separation involves isolating and distinguishing individual components within a mixture for subsequent analysis. Now, the techniques includes chromatography, electrophoresis, distillation, centrifugation, extraction, filtration, ion exchange chromatography, and size exclusion chromatography. Based on the list below, it shows the advantages and disadvantages of preconcentration and separation methods. Now, the selection between preconcentration and separation methods in analytical chemistry hinge on the analysis goals, sample characteristic, and specific requirements. Preconcentration boosts the sensitivity by increasing analyte concentration, reducing sample volume, and selectively isolating the target substance, making it valuable for trace analysis. However, drawbacks include potential losses, sample matrix effects, complexity, and cost. On the other hand, separation method provide advantages such as purity enhancement, selective isolation, and quantitative analysis, but they came with drawbacks like complexity, time consumption, and resource intensiveness. The factors influencing the choice including sample complexity, analytical sensitivity, and time constraint and resource availability. Ultimately, the decision should align with the specific analytical objective and the sample attributes with the consideration of a potential combination of both techniques for optimal results. Now for question and answer, fill in the blanks. The key objective of blank is to enhance the sensitivity of the analytical method. Meanwhile, blank is to isolate and distinguish individual components within a mixture. Now the answer is preconcentration and separation. The key objective of preconcentration is to enhance the sensitivity of the analytical method. Meanwhile, separation is to isolate and distinguish individual components within a mixture.
Now that we are done with the discussion, it's time for a knowledge check. For knowledge check number 1, which statement accurately characterizes the difference between homogeneous and heterogeneous target populations? A. Homogeneous populations exhibit variation in composition at different locations, times, or sample sizes, while heterogeneous populations maintain consistent composition regardless of variations in location, time, or sample size. B. Heterogeneous populations require larger sample sizes for accurate representation, while homogeneous populations can be adequately sampled with smaller sizes. C. Both homogeneous and heterogeneous populations display similar composition patterns in varying conditions. D. The composition of both homogeneous and heterogeneous populations is entirely unpredictable and can vary significantly in any sampling scenario. Due to their diverse composition, heterogeneous populations necessitate larger samples to capture the full range of characteristics and ensure a representative picture. Homogeneous populations, with their uniformity, require smaller samples as individual variations have less impact on the overall representation, hence the answer is B. For knowledge check number 2, which of the following is not a separation technique based on size? A. Filtration. B. Dialysis. C. Size exclusion chromatography. Or D. Centrifugation. Centrifugation works by applying centrifugal force to a rotating solution, causing the particles to move outward. The larger and denser particles settle more quickly, allowing for the separation of components based on their mass or density, hence the answer is D. For knowledge check number 3, you are analyzing a trace metal contaminant in a large volume of wastewater. The metal concentration is too low for direct detection by your instruments. Which technique should you utilize first to improve the accuracy and sensitivity of your analysis? A. Separation alone without pre-concentration. B. Pre-concentration alone without separation. C. Both separation and pre-concentration in series. Or D. Neither separation nor pre-concentration is necessary. The correct answer is C. Both separation and pre-concentration in series. By employing separation first, you isolate the metal from interfering compounds. Then, pre-concentration further boosts its concentration, making it readily detectable by your instruments. This combined approach significantly enhances the accuracy and sensitivity of your analyses compared to using either technique alone. Now that we have finished discussing the sample preparation for analysis, it's time for a summary. Obtaining a representative sample from a larger population is crucial to ensure accurate and reliable analysis. However, simply taking a portion of the material does not guarantee a true picture of the whole. That's where sampling and sampling plan design come in. They are essential steps in ensuring that your analysis starts on the right foot, avoiding bias and misleading results. We also learned that analyte separation is the process of separating one or more analytes from a mixture of other components. This allows for their subsequent analysis and quantification. They have different techniques such as separations based on size, mass, or density, etc. Separation efficiency refers to the ability of a separation technique to effectively separate analytes from each other. And lastly, separation and pre-concentration are both vital techniques in analytical chemistry, but they serve different purposes as we can see on the table below. I hope that you all learned a lot from our discussion today. Once again, we are Team Europium and thank you so much for listening to us.